Folks, hello and welcome to week three. Now that we are coming out of the section on forecasting, we're going to enter into a section on linear programming, linear optimization for the next several weeks. So I thought it would be helpful before we get into any of the homework setups to give this methodology a quick overview and talk about it really at its basic, almost an algebra like level. And I think everybody will appreciate that and maybe take away some of the apprehension about this. If as you've gone through the reading, if this seems a little bit burdensome, really not the case. Is like I said, it really just focuses on a lot of algebra that we've learned over the years, and we're going to apply it here. So you may hear this referred to as linear programming or linear optimization. But just a quick overview here. Uses linear equations and inequalities to model and optimize conditions where relationships among certain variables are known. And that's a key aspect of linear programming, where you have relationships between variables that are known. This is a branch of what we call prescriptive analytics. We're going to be prescribing solutions because we do know the relationships between variables. And I left a little comment here. This is really back to the future with your college algebra. So again, this is all about using linear equations and inequalities to model conditions and solve some really difficult problems in any sort of really industry. Let's talk about what it means for an equation to be, or an inequality to be, linear. And I said here in the second bullet, remember from algebra, we have this thing called the slope-intercept form, the linear equation y equals mx plus b. And in y equals mx plus b, the two variables here are x and y. And if you notice, the implied exponents on x and y are both 1, which makes them linear variables, as we say here. And I say as opposed to something like y equals x squared, where this is a quadratic variable, not a linear variable. Just a quick point for old history's sake. This idea of linear optimization or linear programming is really a branch, or a branch of what we call operations research or management science. Before we've gotten into this period of analytics, but this linear optimization and linear programming technique really became prominent during World War II. As the Allied forces, including the United States, began moving materials to Europe to fight during World War II, and we were trying to optimize these shipments. And this was really the kind of the breakthrough period for linear programming and linear optimization. So, just a bit of history there before we take off here. A couple of key things before we go on to this first type of problem that we're going to look at, really kind of at the root of algebra. Each linear programming or linear optimization problem has three components, every single one of them. It has decision variables, it has what we call an objective function, and it will have constraints. And for our purposes, we're going to solve these linear programming problems using an add-in to Excel called Solver. And I'm going to actually do this week's video in two pieces. I want to do the overview and then go through a couple of homework problems. And as I get into that second homework set, I will show you then how to make sure that you have Solver loaded. So let's, what I want to do very quickly in the last half of this first video, this is a problem that's set up in your textbook in the reading from chapter 7. And this is a typical sort of linear programming problem where it looks like we're trying to minimize the cost of putting together some products. And I'm not going to read down through the whole thing here, but what I want to do is get to the three or four basic things that I talked about. So as you read this problem, what you're going to find out, and like any other sort of problem that we ever did in algebra, each word problem that we did in algebra had decision variables. And so based on the problem here that we're trying to solve, we have defined two decision variables, A being the number of gallons of product A that are going to be used, and then B will be the number of gallons of product B that will be used. So If you recall, remember I said each linear programming problem has three things in common. It has decision variables, right? So these are the things that we need to make decisions about within the problem. And then let's see, the optimization constraint here, or the optimization condition. Let's see, just to kind of bring some light on this. To find the minimum cost production schedule, we formulate the M&D chemicals problem as a linear programming or a linear program, following a procedure similar to the one used for the RMC problem. That's again in your book. We first define the decision variables. And what you're going to find is that production costs are $2 per gallon for product A and $3 per gallon for product B. So in the course of optimizing this condition, what you want to do is to minimize the cost of this chemical composition, where you're using products A and B, where A is $2 a gallon and B is $3 a gallon. So this is the condition that is going to be minimized, again, using the decision variables. Now, again, without getting too deep into the constraints here, this problem is constrained in three ways. It appears that the number of gallons of product A must be at least 125 gallons. So there's a demand condition on the number of gallons of product A that is used. It looks like, let's see, the number of gallons of, product A, number of gallons of product B must be at least 350 gallons. So the total production must be at least 350 gallons. And then it seems to be that there is a processing constraint on each of the chemicals. And it looks like there's a maximum amount of processing time available, which is 600 hours. So it looks like there's 2 hours of processing for each gallon of product A and 1 hour of processing time for product B. And that total processing time has got to be less than or equal to 600, based again on the fact that you have a constraint that that's the maximum number of processing hours that you have available over a certain amount of time. So remember I said that we are going to solve these problems using this solver add-in that we have for Excel. But we could solve this, and really these problems were first solved if you have a condition where you only have two variables. They can be solved graphically. And one of the other conditions that we have here, one of the other constraints that we have on A and B, and it's noted right here, is that we have what's called a non-negativity constraint, which means that both of the decision variables must be greater than or equal to 0. So if you think about, again, more back towards this algebra, let me move this up just a bit here. If you were to draw the XY plane, so if I was to say, well, here is the x-axis where I'm really showing only the values of x that are greater than 0, and this is the y-axis where I'm only showing the values of y that are greater than or equal to 0. What you really are looking at here is the first quadrant of the XY plane. And it's the spot where both variables, both A and B, are greater than or equal to 0. And so what we can do in this, again, what really looks like the first quadrant of the XY plane, is we can come up with what is called a feasible region for this M&D chemicals problem. And what you should take away from this idea of a feasible region is a set of ordered pairs, in this case, a value for A and a value for B, that will minimize this condition while also satisfying these constraints. So one more time, and again, this is the kind of a key concept to go along with decision variables, objective function, and constraints. The feasible region, meaning what is the set of ordered pairs, in this case, values of A and B, that will minimize the objective function, but also satisfy all three of these constraints. And the way that this is done graphically is you're going to note that we're going to graph all three of these we're going to graph all three of these linear inequalities as they appear. But we're going to start by assuming that they're all equalities. So the first one effectively looks like A is greater than or equal to 125. So if you look at this line and assume that this is the A-axis, this is the point at which A would be greater than or equal to 125. And notice that the arrows point in this direction, and just keep that in mind. Then if we graphed A, what would effectively be as an equality, A plus B is equal to 350. That is this line right here, where you note that both of the intercepts, right, the A-intercept is 350 and the B-intercept is 350. And so this would be the line A plus B equals 350, only graphed in the first quadrant. To satisfy the points where A plus B would be greater than or equal to 350, notice what this does is sort of bisects the first quadrant of the plane, but it would be the ordered pairs that are on the line, in fact, actually on the line or above the line, that would make A plus B equal, actually greater than or equal to 350. And then finally, 2A plus B equals 600 is this line right here. And notice that the intercepts, so when B is 0, A would be 300. And when A is 0, B would be equal to 600. So though, again, that's just some old algebra that everybody is familiar with. And that line, again, graphs 2A plus B equals 600. Notice that the arrows here are pointing away, actually back towards the axes, to say it would be the ordered pairs that are on the line or within this area, right, just this area right here, where the value of 2A plus B is less than 600. And so here's what happens at this point. So after I have graphed all three constraints, what I'm looking for is the set of ordered pairs that satisfy all three of these conditions. So I'm looking for all the points to the right of 125, below 2A plus B equals 600, and above A plus B equals 350. And lo and behold, we have this obtuse right angle, or obtuse angle here, this triangle where you have all the ordered pairs that will, again, satisfy these constraints and also have the opportunity to minimize the condition. I will stop right there and just say this. At this point, this is what Excel is going to do for you, or what Solver is going to do for you. And then through its great power, it will find the one ordered pair that will give or make 2A plus 3B as small as possible, but also satisfying these constraints. So for folks, just as a kind of an overview here, again, let me just go back and hit just a couple things real quick here. Remember that when you set up the LP problems or the linear optimization problems, and I'll make this the focus of these two homework problems that I'll do in my next video, but make sure that we're very clear. We're going to want to be very clear about our decision variables. We want to be very clear about the objective function. And then, the real challenge will be setting up the constraints, because that's what, that's what everybody did not like about algebra, right? The word problems and being able to set up the relationships between these variables. And again, that's what makes this a branch of why we would consider it to be prescriptive analytics, because the relationships between the variables are known. We just have to, write them mathematically, typically as a linear inequality. But you'll actually see in one of the problems that I'm going to go through with you in the next video, we'll actually have one that's a constraint that is a linear equality. So I hope that sets the table for the week, and I will see you in the next video. We're going to go through problems 7.41 and 8.29. Thanks.